Semiconductor diodes presented by Dr. K. Srinivasulu. So here, generate first semiconductor diodes, silicon germanium diodes are called semiconductor diodes. So here, Zener diode is a special purpose diodes. Special purpose diodes. Why it is called this special purpose diodes? Let us see now. So Zener diode, what is the Zener diode? The Zener diode is a heavily doped diode which has a result of doping. So in a Zener diode, the doping is very high. So then only it is a very powerful diode comparing to the semiconductor diodes. So here one more important point, semiconductor diodes nothing but silicon and germanium. Silicon and germanium diodes are called semiconductor diodes. Silicon and germanium diodes are called the ordinary diodes. But the Zener diode is a special diode. Why it is called a special diodes? It is a heavily doping. So then only it is a special purpose diodes. Okay, so heavily dope. So impurity material heavily dope in Zener diodes. So that it is very powerful comparing with the silicon and germanium diodes. Has a very narrow depletion region. This allows the diode to be operated in the reverse bias region of the characteristics curve without damaging the PN junction. So here, the Zener diode is always operated in reverse bias direction. Why? Because it is heavily doped. So then only the Zener diodes are operated in reverse bias direction. That is very, very important. But silicon and germanium diodes are operated in forward reverse bias. Especially the Zener diodes are operated in reverse bias region. Why? Because it is heavily doped. So that's why the Zener diodes are operating in reverse bias. So whenever we are operating in reverse bias, that means it requires a heavy voltage. But in semiconductor diodes, that means in silicon and germanium diodes, we want only normal voltage. But in case of Zener diode, we want more voltage. So then only it is operating. Okay, next, Zener effect. What is the Zener effect? The area of Zener diode operation lesser than 5 volts, where the diode maintains a constant voltage output while operating reverse bias. That is one point. Next, avalanche effect. Avalanche effect. So here, greater than 5 volts. So whenever input voltage greater than 5 volts is applied to the diode, while reverse bias, which tends to cause the diode to eventually break down due to heat generation within the lattice structure of the crystal. So here, what is the avalanche effect? Greater than 5 volts. The input voltage greater than 5 volts. Next point. Because of its higher temperature and current capability, silicon usually preferred in manufacture of Zener diodes. Next point. Zener diodes provide a stable reference voltage for use in power supplies, voltmeter and other instruments and voltage regulators. Next, so in this one, the Zener diode symbol is there. Diagram A, ideal diode. So that equivalent circuit diagram here. So diagram B, practically the Zener diodes symbol that is equivalent to one resistor, one diode is there. So this is the in practically every diode is internally some resistor is consisting. Even silicon or germanium or Zener diode, whatever may be, all diodes are consisting internally resistancy. For example, draw the equivalent circuit, equivalent diagram of Zener diode. So equivalent nothing but some resistor is there. Next diagram, characteristics curve of the Zener diode. So here in this characteristic, in this characteristics. So here current and voltage. So in a Zener diode is always operating in reverse bias. That's why some breakdown what avalanche effect and Zener effect would be seen in this Zener diode characteristics. Next, comparison of semiconductors. So semiconductor diodes, silicon and germanium. So the two diodes are comparing with the Zener diodes. So here, this is the general shape is similar. Point of vertical rise is different. Germanium diode is close to the vertical axis. So in this side diagram is consists some forward characteristics and reverse characteristics are shown in this diagram. Compare silicon and germanium diode. Center of the knee means knee of the curve. So knee means operating point. That means threshold voltage. That is minimum voltage. So curve is 0.3 volts for germanium and 0.7 volts for silicon. So 0.3 volts is a cut-in voltage of the germanium diode. And 0.7 voltage is just cut-in voltage of silicon. For example, for taking out in silicon diode, the cut-in voltage 0.7. That means up to 0.7 there is no current. So up to 0.7 there is no current. So whenever the voltage reach to 0.7, automatically the current will be increased. So that 0.7 is called the cut-in voltage. That 0.7 is called the knee voltage of silicon. So whenever you use the silicon diodes, the knee voltage or cut-in voltage or threshold voltage 0.7. In case of germanium diode, the cut-in voltage 0.3 volts. Up to 0.3 volts, the current is 0. So whenever the voltage reached to 0.3 volts, automatically the current will be stopped. So that's why the 0.3 volts is called the knee voltage. The 0.3 volts is called threshold voltage. The 0.3 volts is called cut-in voltage of germanium diode. Okay, are you understanding? 0.3 voltage cut-in voltage for germanium diode. 0.7 voltage for cut-in voltage of silicon diode. Please to remember, very, very important in general point of view. Okay. Next, reverse saturation current is 10 picoamps for silicon and 1 microamps for germanium diode. Next point, the breakdown voltage for silicon is typically between 50 volts to 1 kilovolts with maximum around 20 kilovolts. The breakdown voltage for germanium is typically lesser than 100 volts with maximum around 400 volts. Next, practical diode, silicon versus germanium. In silicon diode, so higher peak inverse voltage approximately 1000 volts. But in case of germanium diode, lower the peak inverse voltage. That means reverse voltage approximately 400 voltage. In case of silicon diode, higher current rating. But in case of germanium diode, the current rating is lower. Next point, in case of silicon diode, the temperature range is up to 200 degrees centigrade. But in case of germanium diode, the narrow temperature range is lower than the 100 degrees centigrade. Next point, in case of silicon diode, higher forward bias voltage 0.7 volts. But in case of germanium diode, lower forward bias voltage is 0.3 voltage. Next, temperature effects in germanium and silicon diodes. So in forward bias region, the characteristics of silicon diode shift to the left at rate of 2.5 millivolts for centigrade degree increase in the temperature. So whenever increasing the temperature, whenever increasing the voltage, automatically the silicon diode is shifted to the left. Next point, the reverse saturation current IS will just about double in magnitude for every 10 degrees centigrade increase in the temperature. The reverse breakdown voltage of a semiconductor diode will increase or decrease with temperature depending on the Zener potential. So depending on the temperature, the current will be increasing or decreasing. The reverse breakdown voltage of semiconductor increase or decrease depending on the temperature. At a room temperature, silicon and GAs, gallium arsenide, have relatively small reverse saturation current. At room temperature, all of you know, room temp 26 volts, 26 volts. Next, ideal versus practically. So in this slide, in this diagram, ideal diode and practical diode. So the ideal diode is consisting of one power supply, one resistor, one ideal diode. Next to practical diode. So characteristics of ideal diode, characteristics of practical diode. So in ideal diode, the current, that means the resistor will not appear in outside. But in case of practical diode, the resistor compulsory will be there. So whenever in this diagram, when switch is closed, the current is passing throughout the circuit diagram. But in case of ideal, when switch is open, there is no current passing. So that is the ideal versus practical diodes. Next, ideal versus practical. Semiconductor diode behaves in a manner similar to a mechanical switch, where it can control whether current will flow between its two terminals. So many times diode is a switch. Semiconductor diode is a switch. Switch is a electronic device. It operates on and off. That means forward bias and reverse bias. That means in forward bias the current is passing. In a reverse bias there is no current passing. That means, so that's why the diode acts as a switch. The semiconductor diode behaves as a switch. The semiconductor diode behaves as a mechanical switch. Switch means, what is the definition of switch? Switch is an electronic device. It operates on and off. So that's why the diode is also working just like on and off. However, the diode is different from a mechanical switch in the sense that when switch is closed, it will only permit current to flow in one direction. Okay, from the characteristics curve, it is evident that there is a resistance associated with the diode which is greater than 0 ohms. However, if the resistance is small enough compared to other resistors of the network, it's assumed that resistance of the diode is 0 ohms. Next, resistance levels. Semiconductor act differently to DC and AC currents. There are three types of resistance are there. DC or static resistance, AC or dynamic resistance. Next one, average AC resistance. So sometimes DC resistance and DC resistance or static resistance. Static means constant, that's all. Dynamic resistance means it is variable resistance. So that's why AC, alternating current, or dynamic resistance. That means the resistor or current will be changes according to our requirement. But in case of DC or static resistance, it is constant. There is no change at all. Okay, next, DC or static resistance. The applications of a DC voltage to a circuit containing a semiconductor diode will result in an operating point on the characteristic curve that will not change with the time. The resistance of diode at a particular operating point is called the DC or static resistance diode. It can be determined using equation number 1.1. RD equal to VD by ID. That means, so here with respect to, so if the time is changes, the current or voltage not change at all. It is a constant. in general, the lower the current through a diode, the higher the DC resistance level. Next, DC or static resistance. Determine the DC resistance levels for the diode of following figure at ID equal to 2 milliamps. So ID 20 milliamps, VD equal to minus 10 volts. Bit A. So this is one problem. So using static means constant. If your voltage or time will changes, but the current or voltage are not changes. At ID is equal to 2 milliamps. VD is equal to 0.5 volts. And thus RD equal to 250 ohms. In previous slides, already given one formula. Simple, using this data into that formula, you will getting the RD. Okay, next B bit. At ID equal to 20 milliamps, VD equal to 0.8 volts and thus RD is equal to 40 ohms. At VD equal to minus 10 volts, ID equal to minus IS, that is minus 1 microamps. And thus RD equal to 10 mega ohms. Next, AC or dynamic resistance. First of all, first you understanding what is the dynamic resistance or AC resistance. That means it will always changes. So DC resistance means that resistance value will changes according to our requirement. The DC value, the DC resistance will be changes. But in case of static, that will not possible because of that is constant. Okay. So here static resistance is using DC input. If the input is sinusoidal, the scenario will be changed. The varying input will move instantaneous operating point up and down of a region. Thus, the specific changes in current and voltage is obtained. It can be determined using the equation RD equal to delta VD by delta ID. So all of you know delta means it will changes. Diode voltage will change. Diode current will also change. Okay. Next. With no applied varying signal, the point of operation would be the Q point. Q point means operating point, cosine point. A straight line drawn tangent to the curve through the Q point will define a particular change in voltage and current that can be used to determine the AC or dynamic resistance for this region of the diode characteristics. Okay, in this two diagrams are there. See, in this diagrams are as shown Q point. So Q point, how to find the dynamic resistance formulas also I shown. So an effort should be made to keep the change in voltage and current as small as possible and equidistant to either side of the Q point. So here define the dynamic or AC resistance. So here determining the AC resistance at a Q point. Next, in general, the lower the Q point of operation, smaller current or lower voltage, the higher the AC resistance. For the characteristics of the figure below, determine the AC resistance at ID equal to 2 milliamps. B bit, determine the AC resistance at ID is equal to 25 milliamps. C bit, compare the results of parts A and B to the DC resistance at each current level. RD is equal to 27.5 ohms. So B bit, RD is equal to 2 ohms, C bit 2. So RD is equal to 350 ohms. So greater than 27.5 ohms. Next to 31.62 ohms greater than 2 ohms. So the derivative of function at a point is equal to the slope of the tangent line drawn at the point. So RT is equal to 26 millivolts by ID. So 26 millivolts is room temperature. So the dynamic resistance can be found simply by substituting the quiescent value of the diode current into the equation. So there is no need to have the characteristics available or to worry about sketching the tangent lines. However, this equation is accurate only for the values of ID. in the vertical rise section of the curve. For small values of ID below the knee of the curve, knee means operating point, knee means threshold volt, knee means cutting voltage. This becomes inoperant. So we sometimes consider the resistance of semiconductor material itself referred to the book Wallstein. Average AC resistance. If the input signal is a sufficiently large to produce a broad swing, the resistance associated with the device for this region is called the average AC resistance. So it can be determined by a straight line drawn between the two intersections established by a maximum and a minimum values of the input volts. So in this diagram, so delta ID in vertical axis, delta VD on x-axis. That means voltage is always taken on x-axis, the current is always taken on y-axis. So average resistance equal to delta VD by delta ID at point. So diode equivalent circuits. Here in this diagram, diode symbol is there. So that diode equivalent circuit diagram is there. So we are with cutting volt 0.7 volt for silicon diode. So average resistance 10 ohms. That is the ideal diode. So in this diagram, the characteristics are there. So the ideal diode establishes that there is only one direction of conduction through the device, and the reverse bias condition will result in the open circuit state. The average AC resistance or smaller average defines the resistance level of the device when it is in the on state. The battery VT, which opposes the conduction direction, appears in the circuit to establish that the silicon diode semiconductor does not reach the conduction state until VD reaches 0.7 with a forward bias. So 0.7 volt means, so cutting voltage, diode voltage across that one 0.7. Next. So here simplified equivalent circuit for the silicon semiconductor diode. Next, ideal diode and its characteristics. So 0.7 volts is the cutting voltage of silicon diode. So whenever the voltage reaches to the 0.7 volts, automatically the current will be going. So up to 0.7 the current is 0. So transition diffusion capacitance. So here diffusion capacitance, transition and diffusion capacitance. So electron devices are inherently sensitive to very high frequency. Most shunt capacitor effects can be ignored at lower frequencies because the reactance capital XC equal to 1 by 2 pi FC is very large. This, however, cannot be ignored at very high frequencies. So X reactance capacitance will become sufficiently small due to the high value of frequency F to introduce a low reactance shorting path. In the PN semiconductor diode, there are two capacity effects to be considered. Both types of capacitance are present in the forward and reverse bias regions, but one show outweighs the other in each region, that we consider the effects of only one in each region. Okay, in the reverse bias region, we have the transition or deflection region capacitance, CT. So CT means transition capacitance or deflection capacitance. So that capacity sometimes is reverse bias. Transition capacitance or deflection capacitance are used in reverse bias direction. So diffusion capacitance or diffusion capacitance or transition capacitance are used in forward bias direction. Please to remember CT transition capacitance, CD means diffusion capacitance. The diffusion capacitance are used in forward bias. Okay, so here the transition capacitance CT are used in reverse bias. Capacitance of parallel plate capacitor C equal to epsilon A by D. Here epsilon equal to permittivity of dielectric insulator between the plates of area A, capital A, separated by a distance B. In the reverse bias region, there is a diffusion region free of carriers that behaves essentially like an insulator between the layers of opposite charge. Since the depletion width D will increase, the increased reverse bias potential, the resulting the transcapacitance will increase. So whenever depletion width is increased, automatically there is no current passing. That means there is no current passing. So although the transient capacitance effect will also be present in the forward bias region, it is overshadowed by a capacitance effect directly dependent on the rate at which charge is injected into the regions just outside the depletion region. So here in this case, the charge carriers will reduce the depletion region and hence will result increase the levels of diffusion capacitance. Next, reverse recovery time. So here one small diagram is there. So TS storage time, TT equal transient interval. So reverse recovery time T RR equal to TS plus TT. Storage time plus transit interval is equal to the reverse recovery time. So in this diagram, so here TS storage time is there, transit travel is there. So whenever these two are combined, that is the reverse recovery time. So diode specification times, data on specific semiconductor device are normally provided by manufacturer in one of two forms. Most frequently, it is very brief description limited to perhaps one page. It includes the forward voltage VF. The forward VF. VF means forward voltage at a specified current and temperature. The maximum forward current IF at a specified temperature. The reverse saturation current IR at a specified voltage and temperature. The reverse voltage rating PIV, RPRV, RVBR means reverse voltage rating, where BR comes from the term breakdown at a specified temperature. The maximum power dissipation level at a particular temperature. Capacitance levels, reverse recovery time TRT, operating temperature range. Light LED, light emitting diode. So the light emitting diode is a diode that will give off visible light when it is energized. So LED and Zener Diode, so here are called the special purpose diodes. In any forward bias PN junction, there is a recombination of holes and electrons within the structure and frequently close to the junction. This recombination requires that the energy possessed by the unbounded free electron be transferred to another state. In all semiconductor PN junction, some of this energy will be given off as heat and some in the form of photons. So in silicon and germanium, the greater percentage is given up in the form of heat and the emitted light is insignificant. In other materials such as gallium arsenide phosphide GaSP or gallium phosphide GaP, the number of photons of light energy emitted is sufficient to create a very visible light source. So here in a light emitting diode, we are using the gallium arsenide phosphide or gallium phosphide. So these are using in making of the LED. LED full form light emitting diode. So the light emitting diode, in a light emitting diode, the PN junction is very, very important. The process of giving off light by applying an electrical source of energy is called electroluminescence. Okay, so here diagram A, process of electroluminescence in the LED. B, graphic symbol of the LED. LED symbol in a B. So next, so here since the LED is a PN junction device, it will have the forward bias characteristics similar to the diode response curves. So LED displays are available today in many different sizes and shapes. The light emitting diode region is available in length from 0.1 to 1 inches. 0.1 to 1 inches. Numbers can be created by segments by applying a forward bias to the proper P-type material segment. Any number from 0 to 9 can be displayed. Thank you for watching this video.